I'm here to talk about updates or remind you of what theme 2A is. And so theme 2A is effectively studying the effect of kelp on physical and chemical fluxes. It's also known informally and locally as in and out. And as we see from in and out, they advertise in and out that there's no delay, but we know that there's a delay, both at in and out, as well as within kelp forests. And so the main idea of theme 2A is to quantify this delay by studying fluxes into and out of the box. So if we think about putting a box around the kelp forest, this is the basic idea of theme 2A, studying this in and out process of what comes in and what comes out. So we're going to start out today. If you've caught this talk last year, not much has changed, but we're going to start out beginning with a section that I'd like to call We Notice. So we'll sort of remind ourselves of the things that we know in terms of the way that the coastal ecology or coastal physical oceanography rather works, and then move into some more recent activities. So we know that water movement in kelp forest is caused by processes at many scales. So if we were to draw a little cartoon of the kelp forest there, and the yellow box represents our sort of conceptual space of where kelp occupies its, where kelp forests find themselves along the rocky reefs. There's the beach on the right side, and then some shelf that may be very narrow in the Santa Barbara Channel, and then out into the deeper channel, and then there's some stratification. This is our physical cartoon. We can think about the idea, and we know that many processes at many scales impact flow through these kelp forests and at the reefs. And this spans, as we move offshore, the relative importance or relative contribution of these influences likely changes. And so we'll just go through briefly to remind you of what we know and understand on some level about these different dynamics. So in general, to remind you, the circulation in the California bight is counterclockwise or cyclonic. So there's the cold California current moving from north to south offshore of Point Conception, and the California countercurrent bringing warm water up from Mexico, from San Diego, and then up through the Santa Barbara Channel. And in general, all of these, the Southern California bight as a whole and all of the sub-basins have these same cyclonic flows within them. And of course, this creates a very interesting gradient in temperature and nutrient availability. Within the Santa Barbara Channel then, mesoscale eddies are a really important transport mechanism. So this is just sea surface or surface currents averaged over the upper meter from the HF radar network. And this is a 6-kilometer resolution here. And so we can see this counterclockwise gyre here. The colors represent faster velocities. Red is up to 50 centimeters a second. These green colors here, kind of like 20, 15 centimeters a second. So we see this large scale, we have these large scale features at the channel scale that are moving material around and bringing material to kelp forests and away from kelp forests. And we know that this cyclonic circulation in both the Southern California bight and the Santa Barbara Channel is caused by a gradient in wind stress. This is illustrated here in this really beautiful image from Melanie Fewing's paper in 2015, where the points here show monthly averages of wind stress from different buoys around the region. And if we just compare the two buoys that are in the channel, 46054 on the west edge of the channel, and then the mid-channel buoy, 46053, we see the length of these arrows represents, or the difference in the size of these arrows shows that there's really strong wind stresses on the outside of the western edge of the channel and weaker wind stresses on the inside of the channel. These arrows also basically are mapped out, averaged by months. And so we see this seasonal pattern here of stronger winds, stronger wind stresses in the springtime versus the fall and winter. And if there's questions or things that you want me to stop and talk further about, feel free to cut in. I don't have my chat up, so if something happens in the chat, you'll have to let me know. So moving on then with this idea of this knowing, we know that these circulation patterns exist. We also know that the modulation and strength of both the strength and position of the North Pacific High creates basically, you could call them seasonal upwelling and changes to upwelling and circulation patterns. And so in the top panel, so the left column here rather represents sort of examples or cartoons of springtime conditions where we have strong winds out of the northwest, versus fall conditions in the right column where the winds tend to be weaker. This is, I use fall loosely. This is kind of midsummer, even into December. And spring may be constrained to just a few months in the now March through June, March through July even. And the top left panel, we see that with strong upwelling, of course, comes chlorophyll or primary production fueled by nutrients that are brought up from that deep nutrient-rich water. And then with the weaker winds, there's less upwelling and there's less biological productivity. These seasonal patterns are also accompanied by changes in general circulation. So the springtime are associated with what we refer to as sort of upwelling circulation, and then subsequent relaxation of flows that go poleward around Point Conception when the wind slacks off. And then there's this general cyclonic flow that can be manifested at different scales and propagate through the channel going along with the mean flow during some of these time periods of weaker wind. We also know that cross-shelf flows, thinking back again to how material can be brought across the shelf and into kelp forests, that cross-shelf flows can be driven by submesoscale features. This is just one example from up near Cambria. The red dot, or the white dot rather, is located there at a kelp forest near Cambria, right near the Rancho Merino Natural Reserve. And the colors represent sea surface temperature taken from a MODIS satellite image. And basically you can see this propagating feature. I've drawn a line across subsequent time snaps of the sea surface temperature to show how this warm water is propagating poleward. And consequently, in the time series plots in the bottom right, you can just focus on the temperature there. The temperature traces in green. These are thermistors that are located at multiple elevations within the water column where that white dot is. And we see that there's a rapid increase in temperature on the order of 2 to 3 degrees associated with the arrival of this warm water from offshore. And so these same processes likely occur, or the same sort of submesoscale pattern or submesoscale dynamics bringing water into the kelp forest definitely occurs in the Santa Barbara Channel kelp forest as well. We also know that local winds modulate transport at short time scales. This is really nice work done by Ryan Walter. And this is just a time series here in the top panel. So this is observations of a set of mooring arrays, or moorings set out in array in up near the Cal Poly Pier, just outside of Pismo, I forget what's north of Pismo. Anyhow, so the top panel here represents the local east-west winds. So it's a time series of the wind. The middle panel shows thermistors arranged the color contours from thermistors that are arranged vertically throughout the water column. And the bottom panel shows the north-south velocities. So red velocities are to the north or into the bay, and blue velocities are to the south or out of the bay. And what Ryan's showing us here in this annotated diagram is that in the diurnal wind picks up, and so the peak of the diurnal wind is illustrated there with a red dot, red dashed line. And associated with this diurnal wind picking up, we see the warm surface water being pushed offshore. So the thickness of that warm layer in red in the second panel gets progressively smaller and smaller as that warm water is transported offshore. Associated with this transport offshore is the intrusion or delivery of cold water at the bottom. So we see the cold water basically increase throughout the water column during this the duration of the wind. The wind slacks off into the nighttime hours, and the result is that eventually we see the return of this warm water basically as this propagating internal wave or propagating gravity wave that comes back, and basically this warm water splashes back into the kelp forest several hours later. Finally, moving along through this diagram, or thinking back to that diagram of these different flows that impact material transport within the kelp forest, we also know that waves drive complex flows through the canopy. And one mechanism that this occurs Obviously, the waves are important when there's really strong storms that in terms of causing disturbance or disrupting and tearing out kelp. But we also can have sort of relatively calmer conditions where there's just small waves, maybe afternoon breezes. There, where the nonlinearity in the surface waves leads to a process known as Stokes drift, where there's a slight transport in the direction of the wave propagation. So this can lead to shear in the water column, which is evident in this photo right here. So we see the canopy flow. We see kelp going one direction, in the direction that the waves are propagating in this case. And at the bottom of the water column, if we look down through the suspended sediment, we can see that there's kelp flowing in the opposite direction of the canopy at the surface. So we know that kelp influences all of these flows, these different processes that I've listed in many ways. This is nice work from Brian Gaylord and Joanna Roseman and many co-authors back in 2007 rather, with work at Mohawk Reef. And so the circles here, the ellipses here represent the primary direction of flow within the kelp forest at Mohawk. So each of these locations is a spot where a current profiler was put out on the seabed, and water velocity was measured throughout the whole water column and then averaged. And then tidal ellipses were computed. So the longer the larger the ellipse, the faster the flow. The direction of the arrow here represents the phase within the flow. So you can see that there's a slight change in terms of the phasing of these flows. But the main thing to take away from this is that the ellipses or the currents are reduced within the kelp forest compared to outside the kelp forest. The other thing that happens within the kelp forest or within this situation is that the flow speeds up around the kelp forest. So we see this mooring that's just to the south of Mohawk here has a stronger tidal ellipse than the mooring that's to the west over here, as the flow impinges upon the kelp forest and is accelerated, just like just as a boat creates a bow wake as it pushes through the water and pushes the water aside. The same thing happens here where the water is diverging around the kelp forest. And then the little bit of water that does go into the kelp forest is slowed down. How are we doing out there in Zoom land? You're having fun?
Woohoo!
Oh yeah.
That's what I thought. Okay, so these are the things that we know. We also know that these continuing on, we know that these changes in flow are seasonal and biomass dependent. So this is further work from Joanna Rosman. And this is work from up in Santa Cruz. And she's comparing in this set of panels here, two different periods of high biomass on the left in the springtime and low biomass in the fall on the right. And the observations here are from a comparison of location 1 versus location 3. So both of these locations are notionally within the kelp forest. But we see that there can be so each axis is a east-west velocity, and so if we focus on the bottom left panel, so these are westward velocities are negative values and eastward velocities are positive values. So this is comparing station 3 to station 1, and if the flows were identical between these two locations, we would expect these point observations, this comparison of the two locations to basically fall on a line that runs 45 degrees through this plot. Instead, there's significant deviations from that 1-to-1 line, showing significantly reduced flows at one location relative to another. And those not only are there reduced flows, but there's basically an asymmetry with regards to the direction. So this attenuation of flow at one location relative to the other location is really significantly impacted by the presence of the kelp. And we see this, or we know this, because when we look and compare it to the October situation where there's relatively less kelp, we start to see these observations move over into this or fall closer onto this 1-to-1 line. Similarly, we know that abiotic variability other measures of abiotic variability is reduced within the kelp. So these are observations of temperature. within the kelp in the top panel compared to outside the kelp in the bottom panel. Each of these sort of, the banding that you see through here represents the result of spectral analysis that's reported here in a period of minutes. And the solid line corresponds to just some a limit of variation that we would expect based upon stratification. So again, within the kelp, the idea here, and then the density, or the darkness rather, of the line represents the magnitude. So what we see is comparing out at all points, basically outside the kelp to inside the kelp forest, we see the reduced variability, or reduced variance in temperature signal inside the kelp compared to outside the kelp. And so you could think of this as basically being the kelp is dampening out internal oscillations associated with water movement that are being manifest and measured via temperature. And this is also shown on the right panel here, with as the result of Fourier transforms of temperature signals inside and outside the kelp, or within the kelp and outside the kelp. And I'll just point out, draw your eye to, again, this comparison of this sort of in the higher frequency section to the right of 10 to the minus 4 hertz, where the outside the kelp bar, or this sort of squiggly line, is above the black part, basically showing that there's higher variance. There's basically more temperature variation outside the kelp than inside the kelp. And we'll come back to this idea of this temperature variance as we move into some of the recent work that we've been doing. Okay, so we know also that flow reductions have consequences for exchange of biogeochemically relevant material. So this is work from John Fram and others here at the Marine Science Institute, going back to 2008. And again, this is comparing outside the kelp forest in the top panel to inside the kelp forest in the bottom panel. It's physical oceanography, so we're comparing velocity observations with the arrows, and temperature observations in the color contours, or the shaded contours that are here. And again, the main take home here is that we can see, if we compare outside to inside the kelp forest, we see this, this reduction in flow evidenced by having these smaller arrows inside the kelp forest relative to the outside the kelp forest. Can also compare the variations in temperature. If we focus, for example, on the hour of the day, we focus in the time period right around 6 p.m. or hour 18. We see, for example, in the outside the kelp forest, we see these really, you can basically think of the contours here as being really noisy and fluctuating up and down a lot. This is similar to this high frequency observation, or this high frequency portion of the spectra that are here on the right side of this plot. Whereas inside the kelp forest, you don't see this same vertical excursion of any particular isotherm. There's a quiz later for all of these plots that hopefully you're taking notes. So ultimately, in terms of the things that we know that forest structure is critical to both how the flow is modified by kelp and the subsequent biogeochemical processes. This is a nice summary by Brian Gaylord and Carrie Nichols and Laura Juergens, sort of summarizing this state of knowledge a couple of years ago from 2012. The plot on the left shows again this idea of attenuation of flow. In this case, this is the alongshore flow attenuation as a function of some kelp density and the distance, how far you are into the kelp forest. And then they've got a nice little cartoon that sort of depicts this range of processes that are occurring. And if we think then back into this cartoon like this of these forest level processes, we can consider that we know that the forest is slowing down water. And we know that back to the sort of little primer on processes that we know are existing in terms of physical processes within Santa Barbara Channel. We know that the mesoscale currents are bringing water to the kelp forest and carrying material away. We know that submesoscale flows are present. We know that local winds are really important and waves are seasonally important. And so the goal of theme 2 activities is really to support the interdisciplinary questions that exist within the rest of the SBC LTER. So to really bring in and combine coastal physics and rocky reef ecology to understand something about biophysical feedbacks and biogeochemical cycling. So our science objectives, our goals here are to quantify residence time in a kelp forest as a function of forest size and density, and also predict typical volume fluxes through a kelp forest based on typical oceanographic conditions. And I point out, or want to tie this idea of typical oceanographic conditions back to this cartoon of these different forcing mechanisms. We know that all these processes are present, but I don't think that we have a really good understanding of how often these different processes are relevant or necessary to model accurately or think about with regards to the history of water or the fate of material that's leaving the kelp forest or coming to the kelp forest. So these are kind of our overarching goals, hopefully with the outcome that we would be able to predict residence time and estimate general flow pathways through a kelp forest, knowing something about these representative forcing conditions and kelp density. So if you could think of these sort of these 4 categories of processes as each being a knob, and depending on how much we turn up each of those knobs, we want to be able to say, well, okay, when the waves are high and the mesoscale currents are in a sort of cyclonic phase versus some sort of mean phase, and this is what happens to residence time within the kelp forest, and this is what the likely fate of material leaving the kelp forest is. So in terms of elements of theme 2, we have a couple of long-term elements, and I refer to this long-term in the LTER sense that we're hoping to be able to inform and have better insight into the existing data that we already have. And so we've added additional moorings at 2 sites. These have been deployed for about 1.5 years now. Or a year and some months. We're hoping to increase hydrographic surveys in conjunction with things in theme 3A. There was no progress last spring, and we're still at kind of no progress right now on that due to limitations in COVID field work. Our short-term elements are to develop techniques to quantify forest structure, and some of that is in progress. Some in-depth work that we've been doing, as that I'll go in and show you here shortly, is that we've examined the role of kelp biomass on cross-shore flows. This is some work that I hope is nearing being ready to be submitted soon. And we're planning for and thinking about some focused experiments with highly instrumented kelp forests in, I left it at 2021 and 2022 because that's what we wrote last year, I wrote last year, but really this is more likely to be 2022 and 2023. So questions about any of that, the sort of the things that we know and the scope of our science goals before I move on to some newer data? Okay, I'll take your silence as a no.
No.
No. Okay, good. Right, now we've got verbal confirmation from Bob. Perfect. Okay, so in terms of these long-term moorings, or I'm sorry, so the long-term moorings that we have are located outside the kelp forest, and these moorings again represent current profilers, ADCPs, acoustic Doppler current profilers, and an associated temperature string that has at a few points dissolved oxygen, conductivity, pH, a few other sensors on there. These are all these sort of like ongoing long-term observations at the decadal scale are all located just outside the kelp forest, just offshore of the kelp forest, as shown here in my little schematic. As part of the idea of theme 2, this in and out idea, we've added additional long-term moorings, both inside and next to Arroyo Camado and Mohawk. And so basically what we've added inside the kelp forest is a sort of paired array that's similar to what's outside the kelp forest, where we've added a current profiler and by we, I mean Clint. Thank you, Clint. As well as a vertical mooring that has throughout the water column that has thermistors and some CTV measurements on it. And we've done this both, as I say, here at both Arroyo Camado and Mohawk. You can see the small schematic here of where each of these locations are. So again, the moorings include thermistors, current profilers, CTDs, and then CFETs and pH oxygen sensors. You can study that. You can ask me for the details of where these are located, but basically what you can, the thing here is MKO and ARQ are the existing long-term moorings, and then you can see basically the inside moorings end at I. So from Mohawk and Arroyo Camado, and then just thermistor strings that are to the east of each of these forests. Our basic goal and hope for these paired long-term moorings is to be able to develop estimates of residence time based on kelp biomass. So going back to our science goal, the basic idea here being that if some flow comes along that impinges upon the kelp forest, in this little schematic here, you can imagine it being some along shelf velocity. If there's some temperature gradient that's associated with that flow, so this temperature gradient is advecting or moving past the sensors inside and outside of the kelp forest. In this case, where the flow is from east to west, we would expect the temperature to increase as this water mass came by. And confusingly, then I've drawn a time series that's opposite of that change here on the right. So here through time, if we saw that some decrease in temperature outside the kelp forest, if the flow is muted and inside the kelp forest, we would expect to be some sort of attenuation of that change in signal through time. And so the hope with these inside and outside moorings is to be able to develop a way to estimate the residence time as a function of these signals. This is just data that I showed last year of an example of temperature moorings from 2018 at Arroyo Camado, showing inside and outside the kelp forest. The different colors represent are associated down in the legend in the bottom left. So the tan colors are towards the surface. The deeper colors are in the deeper moorings, deeper locations rather, on the mooring string are in blue. Obviously, there's not much to be seen at this scale, with the exception of sort of seasonal trends. So the numbers here across in the horizontal axis represent the day of the year. The vertical axis, again, is the temperature in degrees Celsius. So this is going from basically July 1 into roughly October or November. So we can see a slight warming at the seasonal scale. We can see a slight warming, as well as presumably some sort of by eye, just some sort of shift of the period of day 180 to say day 250, sort of being one sort of characteristic period. And then there's some sort of cool down that happens around on day 250 that sort of changes the structure of the ocean slightly, such that there seems to be a less vertical stratification that's associated, less warm. The surface temperatures aren't quite as warm. We zoom in to two representative warming events. So similar to those that warming event that I showed you in Cambria, basically the appearance of a rapid increase in temperature over a short time period. Just contrasting two different events, one in spring with more kelp on the left, the other in the fall with less kelp. Again, the observations from outside the kelp forest are in the top row, inside the kelp forest are in the bottom row. And we see just qualitatively, we can see that there's the inside the kelp forest, the signal is muted compared to outside the kelp forest. So again, we don't see the same level of degree of variability in the trace of temperature at any one of these depths. Particular if you wanted to compare the influence of kelp on damping out and influencing these flows and these temperature signals, you could look right around day 188 and compare outside the kelp forest in the 3 meter, 5 meter, 7 meter, and all the way down to 9 meter observation. You see really rapid changes in temperature associated with internal waves, whereas inside the kelp forest, you don't see these rapid changes, these rapid oscillations. You just see the result of a gradual increase in temperature through time. In contrast, when there's less kelp in the fall, there's still a reduction in these temperature variations, but those reductions aren't necessarily as dramatic or as significant. There's another example we don't have to go into in great detail, but the main thing here is, again, we see a really sharp, or both of these instances are really sharp temperature changes. Outside the kelp, basically you see this really sharp step function at 187.35 and 248.45. Again, those are the day of the year in 2018. Whereas inside the kelp, it takes several hours for this signal to penetrate into the kelp forest. And instead of seeing this really sharp sudden increase, we instead see gradual temperature increases inside the kelp forest in response to this rapid warming event. So this is the exact thing that we're hoping to see in this sort of idea here of that there's a change in temperature, and the response inside the forest and outside the forest are different. So we can take this shift in time series, or this lag in the temperature signal here through time, and we can compute and estimate a lag where there are sharp changes. And as is back in the category of we notice, this lag between these moorings, between the inside mooring and outside the mooring, is related to both how much kelp is there, which is shown in the bottom panel. We see kelp biomass decreasing as we go into the fall, ultimately going away. And this is also these variations in temperature are influenced by the degree of stratification. So the stronger stratification allows signals to propagate faster relative to weaker stratification. And so the plots here just show the strength of stratification, basically just in terms of the temperature difference based between the top and bottom of the mooring, both inside and outside the kelp forest. Okay, so in the past year, obviously we weren't able to do all the field work we were hoping to, but we built upon some of this work with an analysis of cross-shelf flows from the long-term ADCP data. And so this is work that was done by Aurélie Panete. She was a master's student at Insta Bretonne. And so she jumped on a plane 12 hours before in March, or I guess, yeah, late March, early April, 12 hours before the travel restriction went into place, and found her way to Santa Barbara eventually, where we met twice in a park to say hi. But otherwise, she basically did this entire internship remotely. And so she was looking at the impact of kelp biomass on internal wave cross-shelf propagation. And so the idea here, the premise of the study here is it would be analogous to considering how the beach influences the swash along the shoreline. So in this image here, imagine that you have an observation point that's in the yellow star, and the waves are going to come in from the right to the left. This is a picture from the pier on Santa Rosa Island. And the waves don't care what's going on the shoreline. The waves are just going to come in. And so you could think of this as the same situation for our mooring that's outside the kelp forest. So the kelp forest would be over on the left side, sort of representing the shoreline. And there's just some sort of energy that's coming in from the rest of the Santa Barbara Channel. What we want to know about, thinking back to our conversations previously and the things that we want to know about information in the kelp forest. We want to know about the residence time of the kelp forest. We want to know how flows in the kelp forest are attenuated. But all of our long-term observations, our 20 years of observations, are from outside the kelp forest. And so the idea here is there some way that we can link or learn something about what's going on inside the kelp forest from these outside moorings? And so the analogy here would be the idea that the beach somehow influences swash along the shoreline. So in the bottom two images here, we see the wave breaking, and after the wave breaks, it runs up the beach face and then runs back down the beach face, and running in both the process of breaking and running up and down the beach, it picks up sediment. In this case, we see there's lots of suspended sediment that we might then be able to measure at our mooring as a result of this process that happened inshore of the mooring. But you can imagine that if this beach was, instead of being made of sand, as is the case here, if it was made of cobble, then the swash would be very different. There would be much more, a much rougher surface for the swash to run up and back. And so the velocity of that swash would be different. Similarly, the material that gets picked up in that process of running up and down the beach would be very different because there's no sand to pick up if it were a cobble beach. And so we might see some signal associated with the material that's there. And so this is the same idea that we wanted to explore in looking at the cross-shelf flows in the long-term ADCP data. So we got 16-day Landsat data from Tom. So Tom Bell has assembled seasonal observations of kelp, but we wanted to narrow down into the highest resolution. And so I think this was 16-day data. Maybe Tom can correct me if he's here or if I'm wrong. And what O'Reilly did was she created histograms of basically kelp observations based on season. And so she broke things out into winter, spring, autumn, and summer. You can see the distribution, basically the fraction of kelp, number of number of pixels by season there. And then she looked at ways to basically correct and fill in missing data from these Landsat observations. And so obviously where there's situations where there's no kelp whatsoever, it's not possible to reconstruct. But the challenge here was in trying to come up with a local biomass estimate at the highest time series resolution possible. Basically by filling in things both with a linear temporal regression and then this seasonal probability distribution. So this linear temporal regression relies on, if you focus on figure 8 in the top left panel there, you can imagine for all of those locations where there's missing observations, if we were to look at the time image before and or after this particular observation, I can assume that on sort of the monthly time scale, the amount of kelp in that pixel that's missing isn't going to change too dramatically. So if there was kelp in that pixel before this image, there was kelp in that pixel after this image, then we can assume that there was probably kelp in this pixel during this image, but it just somehow got flagged incorrectly. And so that's one way of filling in with this linear regression during this, which works well during the summer when there's high kelp biomass and not too much fog, and we're able to get lots of neighboring images. The other thing then she did was basically taking this idea that what we want to do for the for breaking down these observations into periods of high kelp and low kelp is we don't want to throw out an image like in figure 7 in the bottom left panel there, where there's just a little bit of bad information, because there's still lots of good information there, but we also don't want to bias the result. And so the idea here was just that the missing pixels will be filled in by sort of a Monte Carlo fashion, where we randomly sample from the log normal distribution of the observations in that season and fill things in, so that the statistics of the seasonal statistics are basically used to fill in the individual image, that then from that individual image we can create a time series of kelp biomass. Next thing that O'Reilly did was she took the near surface and near bottom velocities and just averaged them into 2 layers, shown here as a surface layer in purple and a near bottom layer in red. And then these were binned or extracted in a way according to kelp density. So you can see in the different colors there of low and blue, medium and yellow and red. The high kelp basically now have 3 different sort of bins that we're putting observations into. And then from these different observations or these different bins, we're going to do a spectral analysis. And so the result of the spectral analysis reveals the impact of kelp on cross-shelf flow. And I'll zoom in on this, a couple of things within this plot that I'd like to highlight for you in a moment. The blue colors are the surface velocities, the red colors are the bottom velocities, and then the colors that are shaded slightly lighter are lower kelp density relative to the high kelp density. So the horizontal axis is frequency. If you don't like to think in frequencies and powers of 10, you can see that this represents periodicities of 3 days on the top the left edge, moving over to 12 hours, and then into sort of hour scale periodicities over on the right. And the vertical axis is just the variance of velocity. So if we zoom in into this here, we see that there's really no impact of kelp biomass on cross-shelf flows at diurnal or semi-diurnal scales. As we'd expect, there's more variance in the velocity in the surface relative to the bottom. So there's basically, as you move closer to the bed, the influence of friction at the bed slows the water down. So this is confirms what this is a good result here. This is what we hope to see. And the fact that the dark colors and the lighter colors are sort of indistinguishable at both the 24-hour and 12-hour mark, associated again with tidal currents or diurnal winds. This is what we'd expect. We don't expect the kelp to really slow down these really low frequency events. If we look at the high frequency events, though, we see a significant attenuation in velocity. So again, the idea here, both at the bottom and at the surface, the lighter colored bands representing low kelp conditions are higher or are sort of situated above the high kelp conditions in these high frequency areas here. So again, the light blue is above the dark blue, and the light red is above the dark red, indicating that there's increased oscillations, increased energy associated with low kelp conditions relative to high kelp conditions. There still, of course, can be an influence of stratification on this, but the idea here, going back to the idea of the swash zone, is what we assume that we're seeing here is the result of internal waves impinging upon the kelp forest, and then the presence or absence of kelp influencing the sort of the return flow or sort of the back oscillation, if you will, of this internal internal wave, or the rundown of this internal wave. So the significance here, that our hope is that this would provide a means to link these short-term in and out observations to the multi-decade ADCP time series, that we will still be able to say something about internal dynamics within the kelp forest from the moorings that are outside the kelp forest, basically throughout the entire time series. So just a few final slides here of sort of ongoing work or things that we're planning within 2A. A focal point in summer of 2020 was to work towards resolving kelp forest structure with sonar. We obviously didn't do any of that, but Chris Moran in my lab is developing an autonomous surface vessel that we're hoping to be, that will be capable of carrying the side scan sonar and then can be deployed to survey LTER sites. The idea here would be that it would be a sort of easy to deploy, something simple that can be put off the boat and can go and swim around and do a survey while other activities are happening at anchor. Another thing we're doing is we're deploying temperature-enabled wave buoys offshore of 4 sites in the Santa Barbara Channel. So we've already got one buoy or one mooring that's offshore of Campus Point. So this is in 25 meters of water. And we have 2 more buoys that just came in, and we're going to put those at Arroyo Camado and Mohawk. And then when the 4th buoy comes, we'll put that offshore of Carp. So all of these will give us both real-time and then long-term wave observations at these 4 locations, and we'll also have temperature observations down at 25 meters. I put that slide in at 11:58, so I'm sorry I don't have more details about that. And finally, in August, I'm planning to submit a proposal to do this biogeochemical flux experiment associated with the control volume, where we'll try to measure as much physics as possible so that we can back out and understand the sources and sinks within the kelp forest. Skip those in the interest of time, and I'll just highlight other activities in my lab that are ongoing right now. So Cecily Tai is working with Natalie Dornan in Alison Santoro's lab on cross-shelf flows in the nitrogen budget. Luke Carberry is planning some glider surveys in conjunction with theme 3C. And then Jordan Snyder is joining my lab in the fall, and she'll be developing methods to measure flow through a kelp canopy using drones. So with that, I will stop and take any questions.
Thanks, Nick. If anybody has any questions, could you just raise your hand in the chat so we know, or just speak up? Adrian.
Okay, if I ask a question?
Oh, go for it, Dan.
I'm sorry, I can wait.
Go, Dan, you got it.
Okay, okay.
Go.
Great job, Nick. I was just curious, with the mooring data, the temperature data, it's really high frequency. The kelp data is obviously much lower frequency in terms of the data collection. And so is the idea that you just do like a linear interpolation between different, your different estimates of kelp abundance to figure out what the kelp canopy or density is? I mean, how do you pair up the kelp data and the physical data is what I'm wondering.
You're talking about where I was filling in pixels?
No, that's filling in spatially. I'm wondering about filling in temporally. I mean, your temperature data are really high resolution, right? And you have these snapshots of kelp. And so you have a lot of temperature data that is, I don't know, weeks removed from your most recent kelp data, say. So I'm wondering how you pair them up.
Well, I think with the pixel filling stuff that Orally did, we have a time resolution of kelp at least 2 weeks, or almost every 2 weeks. There's obviously some situations where if we get multiple images in a row that don't show up, then we don't have that observation.
Okay.
But some of our premise here is that the kelp only grows so fast, and so it's like it's only going to change so fast, and so if we know something, so I think that the conditions last week aren't all that different from this week.
Gotcha. The one exception to that would be kind of punctuated events like storms that rip everything out.
Sure, absolutely. And I think, and so that's one of the things that I'm excited about with this ongoing wave, with the wave observations, is that we'll start to, I think, get a little more granularity on local conditions of disturbance.
Gotcha. Thanks.
Adrian, you had your hand up next.
Yeah. Hey, thanks, Nick. I was wondering about effect size. And obviously it depends on the critter that you're thinking about. But when I see changes in the environment that are happening as a product of kelp due to various modifications for flow or oceanographic conditions, I wonder what matters to animals. And I know you're a physical oceanographer, so I'm curious about what other people think here in terms of whether that's like plankton or bacteria or fish or anything. Like when we see the changes, differences in the lines of the color lines between like when there's lots of kelp or not very much kelp, what does that mean to you as an oceanographer relative to some of the other powerful forces that are driving variation in oceanographic conditions? Where does the kelp effect size fit in, and is it really big, biologically, but for somebody who's a physical oceanographer, not very big? Or I'm just wondering how you're thinking about that.
I don't know. I don't know if I have an, I don't think I have an answer. I guess that's for you to figure out.
Could I make a comment? It's Sally.
Yeah, go.
Adrian, the structure and I think there's two ways of thinking about the structure in the kelp forest. One is just the advective flow in and the advective flow out. And at that point, some of the zooplankton and larvae would just be passive. But the other thing in a kelp forest is you have structure. So, and I'm actually thinking more the lower forest, but we could think the other part too. And most likely as you have flow past the stipes and all, you set up recirculating eddies. And I'm not sure any of us have ever measured those. And I don't know if any of you divers have done experiments, but that's the kind of location that if an organism wanted to retain or maintain its position, it could take advantage of. So I think that there's multiple scales of motion to look at in order to address your question. Does that help? Yeah. And Nick, I had a thought too. When you show the spectra, and then you can see, well, especially it was with, well, the high frequency movements. And a lot of times at first blush, again, we would think about that as flow in and flow out. And if the motions are attenuated, you might think there's less flow in. I also wondered if we could think about that in the context of loss of momentum. And here I'm thinking the flow is coming in, but it's interacting with the kelp in some manner up in the upper water column or in the lower. And then that loss of momentum, in fact, could be involved in moving the kelp, right? Which again could be important for like dispersal of some of the DOC that's exuded. So I was just wondering, and instead of thinking of it as just a loss of motion, if we could think of it in some way that would be indicative of additional motions that could be caused in the bed. I never thought about that before because I've seen, you know, John Fram did Spectral on the way back when, and we knew that the internal wave motions were damped, but I didn't ever think about it in this other context of like drag, momentum loss.
Yeah, I think that's I think the idea of momentum is right, is a good way to think of it. And I mean, I think I haven't calculated yet, but in theory that, you know, that velocity squared is energy. So we should be able to, that loss in energy has to be, you know, should be able to give us some information.
Yeah, yeah. Because the drag problem, remember Steve's student tried to work on that. And then when you try to do it in a really technical way, too many instruments are required, but this might be another tool that we could use that might be helpful without the huge cost that was involved in that previous experiment.
Yeah, I mean, I think my hope within this is that we're able to do something, or have ways to take ongoing or future experiments and be able to take what we learn and use it in some way back through 20 years.
Yeah, yeah.
Mark had a question, and then John.
Yeah, that was great, Nick. I really enjoyed thinking about that again. I did get myself lost at one point. I was very intrigued by the work your student did in terms of trying to look at the outside mooring data, you know, with the goal of eventually inferring something about the influence of kelp. So I followed along with the spectra and where things were different, surface and bottom. Where I got lost in my head was I didn't quite get how then the measurement's going to reflect what's going on in the kelp. What's the connection that will ultimately be made?
The idea, so my thinking is analogous to, again, going back to the idea of a beach. Imagine a beach that's made of sand, and imagine a beach that's made of cobbles. When the same wave, take a wave that's 1 meter high, when that wave breaks, it doesn't know anything about what the beach is doing. It just knows that it's breaking. And then after it breaks and it runs into the beach, if there's a cobble beach, that water basically runs into all those cobbles and doesn't rush up very far. Whereas if it's a really sandy, smooth beach, then the water runs up a really far distance, and then runs back down really fast because it's really smooth.
So is the idea that there'll be like a shift in that spectrum that's somewhat diagnostic of those far effects?
Exactly. And so the idea is the kelp is like lots of kelp is a situation with cobbles where we don't expect the return flow, the return swash to be very fast because it's been running down these cobbles, versus the situation with no kelp is like a smooth beach where we expect the return flow to be really fast because there's no drag that's slowing it down.
Right. And then you have your time series of actual kelp status that you talked about
Right. And so what we did is we took little like 2-day snippets and said, okay, in this 2 days, is this a period with high kelp or low kelp? And then from those 2 days, we made a spectra, and then we averaged all those spectra that are associated with no kelp and all those spectra associated with high kelp to get those curves.
Okay, cool. Thanks.
Yeah, John?
Yeah, that was very, very nice, Nick. So regarding the temperature data you showed some detailed plots of in and out temperatures. And I was wondering, in the case, particularly the inside temperatures, wouldn't there be some effect of the local heating that goes on? It seemed like that was mostly an analysis assuming advective flows and damping, but wouldn't there also be direct solar heating in the kelp that would also need to be considered in the temperature signal interpretation?
I think absolutely, but also the presence of a canopy would limit how far down that heating signature would go, and also we can calculate. You know, we can make an estimate of how much heating we should expect. We can do that surface heat flux reasonably well, I think.
No, I fully get you can do that. Yeah, but so that would be one. Maybe not so important, but it's certainly feasible, right? Because you know the attenuation and yeah. So it's just one more piece
right.
of that story, right? That's all I was getting at.
Oh yeah, right, absolutely.
Thanks.
I agree. Mm-hmm. Sally?
Nick, back when we worked on the Fran paper, we thought that heating inshore of the kelp forest was affecting the kelp forest heat budget because that was shallower water. And then as it flowed, then it's warmer. So in a way, it might actually contribute to stratification that you might not see as much offshore. So that would be another way to think about it that would extend John's comment.
Right.
But of course, that depends on the proximity of your kelp forest to the beach. And I mean, there's a lot of different factors. You could expect a lot of variability between kelp forests and in that, whether or not you had warmer water coming from near shore.
I had a question, Nick, about your temperature data inside and out and that delay. So are you saying, I was a little confused about, are you saying that that's all a longshore signal, or is that combined alongshore and cross shore?
I don't know, on the examples I showed, I don't know how much of those are longshore versus across shore. I'm guessing that those really sharp sudden changes are similar situations to what I showed from that sequence of sea surface temperature images, where there's some water mass that's basically just being brought in from offshore. But I don't know for sure. I haven't looked at that, but we can figure that out from the current data.
Oh, right. Okay. Yeah, I was just wondering how much of that delay in the signal in the kelp forest is caused by just, time to get to the kelp forest if it's from offshore, versus slowing by the kelp itself if it's alongshore.
Oh, it's very much associated with slowing of the kelp itself, because yeah, it's very much related to the, you can figure, like, we know the distance between the two sensors, so we could figure out what the, how long that should take versus how muted that signal is.
Got it.
Dave?
Dave? I think you're muted, Dave. You're muted.
How is this?
That's good.
Jesus, I have a new computer and everything's, nothing works. I know the UCLA group has been putting into ROM simulations kelp forests. I know Daniel DeHare has been working on this. I'm wondering if the parameterizations that are using there might be something to compare with the observational data sets. Because that seems like it'd be a good synergy, and maybe you guys should be talking to us. Maybe that's all I mean to say.
I agree.
Yep.
All right. Well, thanks everybody. I know we're out of time. I mean, if people wanted to stay and discuss further, that's fine. But thank you, Nick, for doing this. This was really interesting and there's been a lot going on that I didn't know about. So this is really cool stuff.